Greetings to all of you. At the outset, I would like to thank all my subscribers for showing confidence in my channel and for giving me nice comments and encouraging me to go further. Some of my subscribers have asked me about the shooting method technique which is applied for numerical solution of solving boundary value problems involving ordinary differential equations. So it's quite some time that they have asked me about. Sorry for the delay, and I am bringing out the video today. Hope you will all find it useful and you can use it in both your academic and research purposes. So let me begin with my next slide. Let me start with defining what a linear boundary value problem is. The 2-point boundary value problem, as you see here, involves a second order differential equation. We are talking about ordinary differential equation, and the second order differential equation is of the form y double dash is equal to a function of x, y and y dash. So x is your independent variable, y is your dependent variable, y dash is your first order differential derivative. So y double dash is a function of x, y and y dash, and with the limits of x, which is the independent variable, being a and b. So the range of x now is given from the point A to the point B. So this is how the differential equation is first defined in a 2-point boundary value problem. I call it a boundary value problem, so that means there will be some boundary conditions. A boundary value problem has two boundary conditions because we are talking about a second order differential equation, and the two boundary conditions are given this way. The value of y at A is the first end point. So the value of y at A is alpha and the value of y at B is beta. So we are given the boundary conditions, meaning the conditions at the two end points of the independent variable x. So now our aim is to solve this. But before I solve it, let me see what kind of a function should f of x, y dash be in order to be calling it linear. So if f of x, y dash takes the form p of x into y dash plus q of x into y plus r of x, where p, q and r are either pure constants, you could either have them as numbers or they are functions of x, then this boundary value problem which we have constructed now is called a linear boundary value problem. So we are replacing f of x, y dash by this expression so that you get equation 1, and the boundary conditions are continued to be as 2. So 1 and 2 together will be termed as linear BVP, linear boundary value problem. So our motive in this video would be to solve this linear BVP, and the method we'll be using is called the shooting method. So next slide we shall see what the shooting method is and how to approach it and how to use it to solve this system of equations, which is system and then the boundary conditions. So this together, if we call it Roman 1. So the shooting method is used to solve Roman 1. Let me now introduce the shooting method. But before that, let me write down the BVP that we defined in the last slide as y double dash is equal to p of x into y dash plus q of x into y plus r of x as the second order ordinary differential equation, along with two boundary conditions. The value of y at the initial point A is alpha, and the value of y at the final point of x, which is B, is beta. So this is the given linear BVP. The shooting method deals with reducing the BVP into number of IVPs, meaning that if we are dealing with a second order BVP, that means we will be reducing the BVP into two initial value problems. So if we are dealing with the nth order BVP, we can reduce the BVP into n IVPs. IVPs is initial value problems. So as we are dealing with the second order here, we are going to now reduce the BVP into two initial value problems. And how we are going to do that is as follows. Let us now denote y to be equal to y1. Now I have just made this as for my convenience. So wherever I have a y, I shall denote it by y1. So this will be denoted by y1. So correspondingly, we need to see what happens to y dash and y double dash, which are the dependent variables. So what is y dash as per our definition? It is dy by dx. But then y being equal to y1, it could be written as dy1 by dx, which I shall call it as y2. Now we also have y double dash. So what does this mean? Wherever I have y dash, I shall rewrite it as y2. Wherever I have y, I shall rewrite it as y1. Let's see now what happens to y double dash. As per our definition, y double dash is d square y by dx square, which can now be written as d by dx of dy by dx. But what is y written as? Y1 as per our definition, and therefore it becomes d by dx of dy1 by dx. But what is dy1 by dx from the second condition? It is y2, and therefore this becomes d by dx of y2 or dy2 by dx. Therefore, the second order ODE that we presumed will be dy2 by dx, which is y double dash, is equal to p of x into y dash. Y dash is nothing but y2 plus q of x into y. Y is nothing but y1 plus r of x. So this is how the second order ODE is getting transformed to. But what is this y2? Y2 is what we have notated. And what is it notated as? Dy by dx. So dy1 by dx is denoted by y2. Thus, the second order differential equation can now be rewritten as two different first order differential equations. One where dy1 by dx is equal to y2. So this is the one which we have to represent. Now this is the one. The first one is this. And then the second one is this expression, that is dy2 by dx is equal to p of x into y2 plus q of x into y1 plus r of x. So we have now reduced the second order differential equation into two first order differential equations. Look at the boundary conditions. We have not brought it to an IVP still because we have only now initiated the differential equation. The second order differential equation is now written in terms of two first order differential equations. Now what is the next step that we need to do is rewrite the initial conditions. But as of now, we shall leave the boundary conditions at this stage, call the two equations as 3 and 4, and rewrite the boundary conditions in terms of our notation. So what are we calling y as? Y1, and therefore the boundary conditions becomes y1 of a. So this y of a equal to alpha is now becoming y1 of a equal to alpha, and similarly y of beta is b is equal to beta can be now become written as y1 of b is equal to beta. So it is still not reduced into an IVP, but we have now reduced the second order differential equation into two first order differential equations. We shall continue a little further in the next slide and bring it to an IVP form and then see what is the next process. So what we have seen here is the second order differential equation is now reduced to equations 3 and 4, and they represent a system of simultaneous first order differential equations. If you recall the previous slide, we used dy1 by dx, we called it to be y2, we call this equation 3, and dy2 by dx as p of x into y2 plus q of x into y1 plus r of x to represent the fourth equation. And so we have now reduced the second order differential equation into a simultaneous set of two first order differential equations. And what were the boundary conditions? They were still y1 of A is equal to alpha and y1 of B is equal to beta. Note that these are boundary conditions and they are not initial conditions. So when we have a simultaneous first order differential equations, we are aware that if we are given two initial conditions, then we can solve that system of equations using any single step methods. We can use the Runge-Kutta method of the fourth order, or we could use the modified Euler methods, and we have a lot of techniques to solve such equations, but provided you are given the initial conditions as the number of these differential equations we have. We have here two differential equations of first order, so I require two initial conditions. Now that's where we have a problem. Instead of initial conditions, we have one condition at A, one condition at B, and that they are boundary conditions and they are not initial conditions. So in order to generate the second initial condition, now when I talk about initial conditions, all the conditions must be prescribed at A. So what is definition of y of A? Y of A, which I call it as y1 of A, the other is y dash of A, the other can be y double dash of A. These are all the conditions prescribed at the point A. Here I require two conditions. So I will require the value of y of A and the value of y dash of A. So I already know the value of y of A, that is nothing but y1 of A, which is alpha. What I require now is y dash of A, and according to my notation, y dash is y2. So I am looking for defining a value of y2 of A. And is there a procedure to do? It is not always, there's no direct formula in order to do that. In certain cases, yes, there is a procedure, which I will be explaining in my next slide. But mostly, it's only a trial and error process that is required and that's been taken up. What do we mean by trial and error process is we try to guess the value which we do not know. What's the value which we do not know? Y2 of A we do not know. So we try to guess the value of Y2 of A. But if we make a guess, we should be sure of whether if the guess is correct or not. So there should be a condition to cross check. Here the condition that we require, we use is y1 of b. B is the other endpoint. So we check, we make a guess at y or for y2 of a, and we check whether y1 of b is going to give back the value beta. If it gives back on solving the complete IVP, then that means the guess that I have made for y2 of a is correct. So in order to make the guess for y2 of a, I do it arbitrarily. There is no particular procedure. I take certain values, I assume that to be y2 of a, I complete the process of solving the IVP using any of my known tools and ensure that the last value at B gives me beta. If it gives me closer to beta, then I assume that the guess that I have made for y2 of a is correct. Else I have to keep trying out certain different values for y2 of a in such a manner that y1 of b is equal to beta. This method is the main crux of shooting method, as we are not able to judge the value of y2 of a directly, but we are shooting it around a particular number in such a manner that this last boundary condition is satisfied. Since we are shooting and trying to go closer to that boundary condition, the method is called shooting method. But because we are dealing with a linear BVP, reducing it to a linear set of two first order differential equations, there is a simpler method of defining y2 of a, the procedure for which will be explained in my next slide. Let us now find the procedure to find the second condition. If you ask me if this procedure is common for every kind of problem, the answer is no. Here we are dealing with a linear BVP, and thus we are able to use a concept called linear interpolation to find or create a formula which will give us the required result. But then this may not be directly applicable for especially when the BVP is highly nonlinear, or we deal with coupled kind of equations. But this is an idea which can be implemented even for higher order differential equations. So our motive in this case is to find out the value of y dash of a, or which is y2 of a. So that's the main motive, and for that we make an attempt. We call the first attempt to be trial 1, and we choose a value for y2 of a. The value that we choose for y2 of a is guess 1, meaning the IVP now that is completely defined, it will be containing equations 3, 4, and what are the two initial conditions that we will have now? Y1 of A, which is alpha, is already known to us, and Y2 of A, which is what we are assuming now in terms of trial 1, we call it guess 1. So now the IVP is complete, having two first order equations and two initial conditions. So the procedure now would be to solve it using any of my known tools. The best would be the RK method of fourth order, and I will proceed to solve it and check whether y1 of b, the value of y1 at b, should be actually beta. So by taking the guess value as guess 1 for y2 of a, am I getting beta for y1 of b is my check. Assuming that I don't get beta directly, but I get solution 1, because it's a very hard thing to guess the value exactly in order to get the second boundary condition satisfied. So let me assume that for the guess that I am making, the solution or the value of y1 of b is solution 1. In a similar manner, what I do is take the second trial, take the second guess. So here instead of guess 1, what am I going to take up? I'll take another wild value, and let me assume that the second guess is taken for y2 of a, and I solve the problem because the IVP is complete, and let the solution for y1 of b be solution 2 rather than beta. So we are not sure whether it is beta. So what have we tried now? Beta is actually our target. The target is to get y1 of b to be beta. But then where are we trying? We are assuming value as guess 1 for y2 of a, guess 2 for y2 of a, and trying to solve the problem. By solving the problem with guess 1, I am reaching somewhere here, it is say assuming it's coming to solution 1, y1 of beta. B is not beta exactly, but it is somewhere we are arriving at this point, say. And by taking guess 2, say we are arriving at some other value, say solution 2. So we can now judge that the value, if it is guess 1, we are arriving at solution 1. Guess 2, we are arriving at solution 2. Both are farther from beta. So our guess would be that if we interpolate it linearly and take a value somewhere here called guess 3 and then solve the problem, we will arrive at the result that we want, which is our beta. So, and that is where we are targeting. So this guess 3 can be determined knowing guess 1, guess 2, solution 1, solution 2. We can guess this 3, guess 3 value by using our linear interpolation formula as guess 2 plus m times, I'll tell you what m is, target minus solution 2. Target is our beta. Solution 2 is what we get in the second trial, and m value would be the difference of the guesses in the numerator divided by the difference of the solutions in the denominator. So once we use this linear interpolation formula, then we will be able to obtain the value of guess 3, which will be chosen as y2 of a, and once the problem is complete, the value that we'll be getting will be very, very close to the target beta. So since we are trying to attempt two methods, two trials, in order to shoot and get answers, and our goal is to reach at this beta. This shooting procedure is the main crux of the shooting method. So the value of beta can be directly achieved using the linear interpolation formula. I repeat once again, this is possible because the problem is a linear BVP. It may not occur or be satisfied for complicated differential equations. So now we have found the two initial conditions as y1 of a equal to alpha, and now we have comfortably can say that y2 of a is not guess 1 or guess 2, but it is guess 3. So together with equations 3 and 4 and with the two initial conditions, we are able to declare, right, the given IVP in this manner. The 2-point BVP is now completely converted into a system of simultaneous equations this way, and then forwarded by the two initial conditions with guess 3 allocated for y2 of a. So this complete system is now solved. Now this could be either solved, it can be done manually. You have a lot of packages available even in Matlab, which I will be using Matlab here to show you, where we use ODE 45 package in order to solve it and guess the result, and can be done even using Mathematica and to check whether our y1 of b is equal to beta. This is the procedure. Let's apply the procedure to a problem in our next slide. Let me start with a problem where I need to solve y double dash plus xy dash minus xy equal to 2x. So it's a second order ordinary differential equations, as you can see here, with two boundary conditions, y of 0 equal to 1 and y of 2 equal to 8. So the range of x is from 0 to 2. So our condition that we have to check, that beta that we have here is beta is nothing but 8, and the value that we want, that b value here is 2, a value is 0, alpha value is 1. So let us proceed with the procedure that we defined in the previous slide. First step would be to reduce the second order ODE into two first order ODEs following the same procedure. Let's start with the substitution. Let y is equal to y1, so that y2 that we y dash that we define as y2, y double dash is dy2 by dx. But what is our differential equation? It's y double dash plus xy dash minus xy equal to 2x. So what does that mean? I can rewrite now y double dash to be equal to x into y minus xy dash plus 2x. Now as per our notation, this y double dash is nothing but dy2 by dx, and then right side x will remain x, y becomes y1. Here x will remain x, y dash becomes y2 plus 2x. So that's what we have got in this particular equation. So the two differential equations that we finally get will be dy1 by dx, this one, which is equal to y2, and dy2 by dx is equal to xy1. This one that I have written, that is written here, xy1 minus xy2 plus 2x. And we of course have the same boundary conditions, so far no change. So let's move to the initial condition construction in my next slide. So now we are supposed to find the value of y2 at 0. This is what is my unknown, first of all. Second initial condition that we have to make a guess. And what is the condition that we have to check? That y1 at the second endpoint, which is 2, should be equal to 8. So this question mark is to be judged by taking two guess values. So our unknown is to first find the initial condition at y2 at x equal to 0. So we want to make a guess, and in such a manner that y1 of 2 is equal to 8. Let's make a guess. You could also try it by any method. I have taken up that let the first value be 1. So this is my guess 1. So I am taking y2 of 0 to be 1 initially, so that I have this system completely in this manner. dy1 by dx is y2, dy2 by dx by the given equation, and look at the initial conditions. This is already given to us. This is given, and this is what we have assumed or guessed, y2 of 0 equal to 1. And now I am going to use the ODE 45 package in the MATLAB package, and then check what is the solution 1. What do you mean by solution 1? Solution 1 is the value of y1 at the value 2, and that has to be actually 8. But that what is actually 8? It's not so. What's the value that we are getting? We are getting the value 6 instead of 8. So by using my y2 of 0 to be 1, the solution that I am arriving at, which is at the other end point at 2, at 0 I am guessing that y1 of 2, y2 of 0 is equal to 1, and I am getting the value of y1 at 2 to be 6. But actually it should not be 6. What should it be? It should be 8. And therefore, I get one result, that if guess 1 is 1, then solution 1 is 6. Now let me make the second trial and choose what is my second guess. Before going to the second solution, I would like to show you a screenshot of the Matlab program that I had written, and to show you that the value of y1 that I am getting here at the end point at 2 is 6. You can also check it in the graph, that the value of y, that value of y1 that we are looking at, the value of y or y1 at the point 2, here it is giving you the value 6, whereas it should actually give you the value 8. So this is a small program that we have written using the syntax of Matlab. And now let's move on to the second guess and see what happens. So we have seen by guess 1 being equal to 1, we got the solution 1 to be 6, not 8. Now let's see what's the second guess I'm making. Second guess, I take y2 at 0 to be 4. So I define the complete IVP as a system of two first order equations. And now this is the value which is already given. And this is the value which we have assumed. This is what we have assumed. So what are we getting by using ODE 45 in Matlab? I'm getting solution 2 to be 11.9587. So it's way beyond 8. It's greater than 8. So in taking guess 2 to be 4, my solution 2 here is 11.9587. So what did I want to actually shoot? My target here is 8, right? But I have made a solution of 1, arrived at 6. I have made a solution, I have guessed the solution as 4, and I have arrived at 11 point some value, 9587. So now I make use of the linear interpolation to guess a value here, so that I choose that for my initial condition. And let me check if I am getting closer to 8. Let me do that in my next slide. Now this is the screenshot of the second trial that I have made. So I have taken the value here as 4, as you can see in the program. And what is the final result I get? I get 11.9587. So you see, at the point 2 for y1, the value that I am reaching is not exactly 12, but because of the scaling here, it's somewhere very close to 12, but not exactly 12. So that's the value I get for my second trial. Now the time has come to use the linear interpolation formula, which I shall show you in my next slide. So let me start with the linear interpolation formula to find what is my guess 3. I shall start by finding out the value of m, guess 1 minus guess 2. As you can see, my guess 1 value was 1. Guess 2 value was 4. The solution that I got for 1 was 6. The solution that I got for 4 was 11.9587. Simplifying, I get the value of m to be this. Now I use this value of m in my formula to derive guess 3 as guess 2 plus m times target. Target is what I actually want, which is 8. minus solution 2. All the values are known to me. I substitute, I check the guess value. I have taken it correct to 5 decimal places. So guess 3 value is almost nearing 2, or it's closer to 2. So it's 2.00691. Now let us check whether, if by taking guess 3 to be this value, will my end result, which is y1 at 2, will it be equal to 8 or closer to 8, is our check, if by taking it for guess 3. If guess 3 is equal to 2.00691, will this be satisfied? Yes or no? We shall apply this in our Matlab tool again and check. Kindly note that by taking this 2.00691 as my value for the second initial condition, please note that the value of y1, which is y for us, is 7.99999, which is approximately 8. So I have almost got the answer, and now the problem is complete. So this shooting type of a technique that we need to see is by making two wild guesses and using the linear interpolation formula to get the required, to reach the required target. So what is finally done is the system of simultaneous first order differential equations given in this manner was solved with two initial conditions, where one was given to us in the problem, the other was obtained using the shooting technique. And by running the program, we find that we get values of both y and y dash, which is y1 and y2, at values lying between 0 and 2. Kindly note that the step size that was considered here was chosen automatically by the OD45 software, and we find that accurately the result was satisfied at the second endpoint. So this completes the problem. I hope this problem is clear. I've tried to explain the concept of shooting method in a linear BVP, but this could be extended to other kind of boundary value problems too. I hope I could give you the gist of this method, shooting method, through a small description and an example where I have taken up a linear BVP. But this concept of shooting technique could be used even for nonlinear or coupled kind of differential equations, either ODE or even PDE. Since we are all using packages, we could also write a simple C program and run it to check whether our guess values are right, because we are checking the last value in all the guesses. So it can be done for any kind of system of equations of any order. So a very highly applicable method this is, and I hope it will be helpful to you for both academic and research reasons. Thank you. God bless. Take care.